Hey, welcome back. In our last video, as you might recall, we introduced the big question in chemistry. That is, will this reaction happen? If not, why not? One way of saying that is the reaction thermodynamically favorable? Basically, that's a fancy way of saying it happens. We also found out one useful test to see if something is thermodynamically favorable, and that was the idea of entropy, represented by the letter S. As you recall, entropy is basically the disorder of the system, or the dispersion of energy and matter of the system. Now, entropy was useful because we said that for any process that happens spontaneously or is thermodynamically favorable, the entropy change of the universe is positive. If the entropy change of the universe was negative, then the reaction would not occur, at least not without you providing some extra energy to make it happen. Today then we're going to move on and find another test to determine if something is thermodynamically favorable, and that is a free energy. A very, very useful idea in chemistry. Before we get to that though, we need to review some thermochemistry, specifically some enthalpy. As you recall, delta H represents enthalpy, and enthalpy is basically usually just heat energy that's gained or lost in a reaction. There are two types of reactions then, exothermic and endothermic. For exothermic reactions, heat is released. You can think of it as a product, and in that case, your delta H, or your change in enthalpy, will be negative, less than zero. The other type of reaction is an endothermic reaction. In that case, heat is absorbed by the system, and as you'd expect, the delta H is positive or greater than zero. So with those things in mind, we're going to move on and talk about this free energy thing. Free energy is also known as Gibbs free energy, named after the American chemist Josiah Gibbs, who first came up with the idea. It's called free energy. Free doesn't mean doesn't refer to cost, as in it's free and you don't have to pay for it. Rather, free means available, as in energy that's free to be released and can be used to do work. You engineers out there will be especially interested in this because that's what engineers want to do. They want to use the energy of a system to do work, such as push a piston like in your car, lift a weight, or light a light bulb, or something like that. And so free energy is the amount of energy that can do that. Heat energy is one component of free energy, but it's not the only one. There's also entropy involved too. And so the free energy of a system is represented by G, and the equation for it is H minus temperature times the entropy. Free energy is a state function, meaning that it doesn't matter how you get there. All that matters is where you started and where you ended up. And so usually for state functions, we're only interested in changes in these things, and so we're going to see a lot of deltas or triangles. And so this is the form that we most often use. The free energy change of a system is equal to the enthalpy change of the system minus the temperature times the entropy change of the system. If you were doing the reaction at standard conditions of 25 degrees Celsius, 1 atmospheric pressure, we have the further special case shown in the box here with degree signs. So the standard free energy change of reaction is the standard enthalpy change minus temperature times the standard entropy change. So why do we worry about this thing called free energy? Well, that's actually a very, very useful idea in chemistry, and it's useful because it tells you very, very quickly whether or not a reaction is spontaneous. Is it thermodynamically favorable? And so the nutshell, the second thing to remember, the first is this equation, the second is what it means, and that if a reaction has a free energy change of less than zero, then that reaction is thermodynamically favorable, and it will happen. It will go until it reaches equilibrium, whatever that equilibrium will be. In other words, the reaction works. So again, if you have a negative free energy change, a negative delta G, the reaction works. It's a good, effective reaction. And so this should kind of make sense. If a reaction has a negative free energy, then it will go as low as possible and release some of that energy out into the world, and the release of energy is negative. So the next question might be asking, why free energy? Why not just stick with entropy? Why use free energy instead to predict the spontaneity? Well, there's a good explanation for that. We've already talked yesterday about how the entropy of the universe must increase for a spontaneous process. But as you can imagine, the universe is a really big place. This entropy change could occur anywhere in the universe. It could occur in the immediate surroundings of your beaker or flask. But in the case of photosynthesis, for example, the increase in entropy could be 93 million miles away in our sun. And so it's very, very difficult to keep track of the entire universe. And so free energy, on the other hand, is entirely from the system's point of view. All we have to worry about is what we're looking at, the beaker, the flask on the table. So all we have to do is look at the enthalpy change of our system, the entropy change of the system, and the temperature of the system, and that's it. We don't really care about what happens in the rest of the universe. Furthermore, free energy is also closely related to equilibrium, and we'll get a nice equation that relates the two of them very simply. And so free energy is a useful method to determine if a reaction is thermodynamically favorable. So let's do an example and try it out. So here we have what's called the dimerization of nitrogen dioxide. Nitrogen dioxide, you might recall, is our brown death gas. We often make it when we combine nitric acid with a metal to create that brown choking gas. Well, if you have two of those gas molecules, they can join together to make N2O4, dinitrogen tetroxide. We are given the enthalpy change and entropy change of the reaction, and now we're asked to predict the sign of the reaction's free energy change, enthalpy change, and entropy change, and determine if it's spontaneous or not. For a moment, let's just forget about the values up here that I already gave you, and let's just try to focus on these predictions. Can you predict the sign of the reaction's delta G? The answer is no, not just by looking at it. It's pretty much impossible to do that. Similarly, you can't predict just by looking at the reaction whether or not the reaction is going to be endothermic or exothermic. You might have some hunches, but you really don't know until you either do the reaction and observe it, see if there's heat released, or if you crunch the numbers and calculate it. You can, however, determine the entropy change of the reaction. We did that yesterday. In this case, we have two particles going down to a single particle, and so you would predict this to be a negative change in entropy. Lastly, can you predict if a reaction is spontaneous or not? Can you predict if it happens, if it's good? The answer is no, you can't do that either. You might be wondering, wait a second, I thought we said that if the entropy change was negative, then the reaction was not spontaneous. Well, not exactly. You see, that was the entropy change of the universe. That must be positive in order for it to be spontaneous or thermodynamically favorable. What we found, however, is not the entropy change of the universe. This is the entropy change of the system. Two different things here. And so, no, we cannot determine if a reaction will be spontaneous or not because, again, there's no way of looking at the entire universe. So with those predictions in mind, or the whole one prediction, let's go ahead and calculate some of these things. Part B, is delta H favorable for the reaction? Let's take a look at the free energy reaction equation. We said that we want delta G to be negative in order for our reaction to work. That means that we want delta H to be negative as well, because that will give us a negative number on the left side. So looking up at our enthalpy change here, it's negative 58 kilojoules, so yes, that's favorable. Exothermic reactions are favorable for spontaneity. Not all exothermic reactions are spontaneous, as we'll see, but if it's exothermic, that is a good sign. Is the entropy change favorable? Well, we already said our entropy change was negative here. If you look at our equation, if we have a negative entropy change, that's being multiplied by the temperature, which has a big old subtraction sign parked out front. As you know from math class, two negatives will make a positive. And so we have a negative enthalpy change and a positive term over here. This positive, that's bad for spontaneity. Right? So if entropy decreases, that's bad. And so a negative delta S means that's not favorable. It can still happen, but it's not favorable. The question is the enthalpy change, the delta H, is that negative enough to overcome the positive delta S? The negative delta S. And to see that, you really have to calculate it. So let's go ahead and calculate it now. So our standard free energy change will be equal to our enthalpy change, which is negative 58 kilojoules. If you notice, our units up here, our delta H is in kilojoules and our entropy is in joules. Those have to match, otherwise we're going to get a wrong answer. So let's go ahead and convert the kilojoules to joules. So that's negative 58,000 joules. We're going to subtract the temperature at 298 Kelvin. That must be in Kelvin. And then we're going to multiply by the entropy change. That entropy change is a negative 177 joules per Kelvin. Notice when you multiply it out, the kelvins cancel out. We're going to be left with joules, which will add or subtract nicely to our delta H. And so, moving on, we have negative 58,000 joules minus a negative 177 times 298, which will give us a positive 52,746 joules, which gives us a grand total of negative 5,254 joules, which rounded to the correct sig figs would be negative 5,250 joules. So there you go. Our delta H was negative enough to overcome our entropy change. So is the reaction spontaneous? All you have to do is look at the sign parked right in front of delta G. It's negative, so yep, it is spontaneous. Okay, so we've established that delta G is negative at 298 Kelvin, and therefore the reaction is thermodynamically favorable. But what about other temperatures? Well, with other temperatures, that number will change. And so in part D, we're asked, should the reaction be done at high or low temperatures to ensure the reaction is thermodynamically favorable, and justify your answer. To do this, we'll just think about the equation, which you should commit to memory. It's given to you on the equation sheet, but it's a pretty simple one and very useful, so it wouldn't hurt to go ahead and poke that in your noggin. So we want it thermodynamically favorable, which means that delta G must be negative. We know that delta H for the reaction is negative as well. And we know that delta S is negative as well. So of those two terms there, the delta H is favorable for spontaneity because it's negative, and delta S is unfavorable. So basically, we want to minimize the entropy change here to minimize that bad effect of the decrease in entropy. So to minimize this, we're going to want to do this reaction at very low temperatures, ideally, such that when we multiply the low temperature by this negative sign and then subtract it, we're going to end up with a smaller positive term instead of a larger negative term. And so we want to do this reaction at lowest temperatures to minimize the positive delta S, the negative delta S. So we can go ahead and calculate what temperature exactly this reaction is no longer thermodynamically favorable, what reaction it no longer happens, what temperature it no longer happens. So to do that, we again go back to our equation. Now, of the four variables there, delta G, delta H, T, and delta S, two of them are assumed to be constant and two can vary. The constant ones would be the enthalpy change, delta H, which we know is negative 58,000 joules. The temperature is variable, so that's going to be our unknown here. And the entropy change, that is also a constant, negative 177 joules per Kelvin. So again, we assume that delta H and delta S are always the same, always constant at any temperature. The temperature, of course, varies, and so does the delta G. To determine when the delta G is no longer positive or negative, delta G would be 0. And so that's kind of the threshold, the cutoff point for when the reaction is spontaneous and when it's not. And so now we're all set up. We're just going to solve for temperature. So you can do that, and you get a temperature of 328 Kelvin. As you recall, you can subtract 273 to get it into Celsius, and so that would be a temperature of something, 55 degrees Celsius. And so again, if you imagine a thermometer, excuse my drawing here, if you imagine a thermometer, we're at 328 Kelvin, and anything above that temperature, your delta G is going to be negative, and your reaction will not be spontaneous. Excuse me. Let me walk that back. Your delta G will be positive, and your reaction will not be spontaneous. Anything below that temperature, the reaction will be spontaneous because your delta G will be negative. So one more time, the cutoff for this reaction is 328 Kelvin, because that's where your delta G becomes 0. Anything above that temperature and your delta G will be positive, the reaction will not be spontaneous. It will not go well, maybe a little bit, but not much at all. And anything below that, your delta G will be negative, and the reaction will be spontaneous or thermodynamically favorable. You can see this with your own eyes in these pictures shown right here. Again, NO2 is the brown death gas. It's called brown death gas because it is brown, as shown over here on the far right. And here we have a temperature of 20 degrees Celsius, and your thing looks quite brown. As you cool it, however, the reaction of 2N2O going to N2O4 becomes more and more spontaneous. And so as you cool it, the brown death gas is going to turn into N2O4, which is actually colorless. So as you cool it down, the system becomes less and less brown, more and more colorless as you form more and more N2O4. So that's one example of free energy at work. So let's go ahead and summarize some of these big picture ideas here. Again, we want delta G to be negative, and so let's look at all the possible combinations of how we can get a negative delta G. Basically, there's two variables, each of which could be positive or negative, and so we have 4 different combinations in total here. The first one is if delta H is negative, exothermic. As we said, that is a good thing for spontaneity because we want delta G to be negative, and entropy is positive. That is also a good thing because that will turn this whole second term into a negative quantity, and a negative will give us a negative always. So for a reaction, if it's exothermic and entropy increases, the reaction will be always spontaneous at all temperatures. On the other hand, if it's exothermic but entropy decreases, again, exothermic is good, a decrease in entropy is bad, so we want to minimize the delta S term, and so we're going to use low temperatures instead. Then flipping over for an endothermic reaction, that's bad. That will give us a more positive delta G, but an increase in entropy, well, that's good. So therefore, we want to maximize that, and so we're going to want to maximize our T delta S term, so we're going to run this at high temperatures instead. And lastly, if it's endothermic, that's bad. If entropy increases, that's bad. And basically, this is a hopeless situation. This one ain't going to happen. This is a big fat never. At least not without a lot of help from you putting some energy in or something. It will happen a smidgen little bitty bit, but just not significantly. So therefore, if you know the enthalpy change of the reaction and the entropy change, you can make some predictions about when the reaction will and will not be spontaneous and what you can do to make it go better. So we'll just take a more quantitative look at this then. And we'll use the same ideas, but with some numbers instead. So in part A, delta H is a negative 10 kilojoules, so that will be a favorable process. Delta S is negative, that is unfavorable. And so when is the reaction thermodynamically favorable? What temperature range are we looking at? Well, we'll go ahead and plug in the numbers. Again, using our equation, delta G equals delta H minus T delta S. We're going to plug in 0 for delta G to find the cutoff point, and plug in negative 10. We're going to go to joules, so negative 10,000 joules for our delta H, minus our unknown temperature times our entropy change of negative 10. You solve for temperature and you get a whopping 1,000 Kelvin. So we want to minimize our delta S term, and so we're going to do this at lower temperatures. So this reaction will be spontaneous for any temperature less than 1,000. As it gets colder and colder, it'll become more and more spontaneous, more and more thermodynamically favorable. I'm going to take a moment and go ahead and fill out the rest of the chart. You can do it too, and then we'll compare answers at the end. Okay, looking back at our results here, we saw that part B will never be spontaneous, because if you try to find a temperature, you get a temperature of negative 1,000 Kelvin. As you know, you cannot go below 0. That's absolute 0. And so this reaction will always be non-spontaneous. It will not be thermodynamically favorable. On the other hand, part C, we end up with the temperature of 1,000. This time we're going to want to maximize our entropy change, and so we're going to run this thing at high temperatures, so we're looking at temperatures above 1,000 Kelvin. And lastly, in part D here, it will always be spontaneous no matter what temperature you use, because you'll always get a negative answer. Okay, one last example. This kind of puts everything together that we've been talking about. We have the combustion of propane to make CO2 and H2O. We're going to balance the equation, figure out our delta H values and delta S values, and then combine that into our delta G value. I'll go ahead and work through the first part. We'll compare answers, and we'll find out our delta G too. Okay, looking back at our results, we get a delta H of negative 2222 kilojoules, which is a very, very favorable enthalpy change. As you know, it's combustion. Combustion releases a lot of heat. That's a good thing. For part 3, the entropies, we get an entropy change of negative 373 joules per Kelvin, which is not favorable. And looking at the balanced equation, we can see why. We have 6 moles of particles going to 7 moles of particles. However, if you look at the phases, we have 6 gas particles on the left side, and on the right side we only have 3 gas particles and then 4 liquid particles. The phase thing is most important here, so we're losing gassy particles, so that leads to our negative change in entropy. Looking back at how we calculated it, you notice that in both cases it's products minus reactants, products minus reactants. Similarly, you have the same coefficients as well. 3, 4, 1, 5, 1, 5. Really the only thing that's different besides the values is the fact that, well, 2 things. One is you can have negative heats of formation, but you have positive entropies. You'll never have a negative entropy. Again, the lowest entropy you can have is 0, and that's for perfect crystal absolute 0. And then secondly, if you look at the elements, for O2, for example, the heat of formation is 0, but it does not have an entropy of 0, as an entropy of 205. So with these delta H's and delta S's in our pocket, we'll go ahead and put those together in the equation and figure out if the combustion of propane really is spontaneous or not. So I'll be right back with that. Okay, did you get a delta G of negative 2111 kilojoules? Hopefully. Looking back here, so our negative delta H is quite large, and even though we have a negative delta S, which turns into a positive term here, that positive term is really small compared to our very large negative term here. And so the delta H swamps the delta S term, and our free energy change is very, very negative, negative 2111 kilojoules. So it's very thermodynamically favorable. This is the free energy that's available to use to do work. You can use this to heat your home. You can use this to power your car or a forklift. You can use it to make the world a better place. So there we have it for our second lesson on thermodynamics. We have a brand new way of determining if something is thermodynamically favorable or not, and that's to use this handy-dandy equation right here. In our next video, we'll learn some other ways to find delta G, and then we'll tie it all into equilibrium. So until then, I'll see you later.